Welcome to RStudio. This is your RStudio setup. This is the console where code goes. This is the environment where you're going to find your stored data and functions, and this is where your plots appear. To first start with R, we need to make a new file and get an R script. Here you'll see a window pop up. This is where we write code because we can modify it. Hashtags, which is this right here, mean that this code won't run in the console below. Only code without the hashtags can be run. To save your R script and run it later, you just need to click on this little save icon. We can go to my desktop and we can save it as Wild Dogs, which is the first example. I can always reopen this script. The first thing I have to do is open my file. If you go to the RTutorial, you will find this code that you can copy and paste. This part is what you actually want to name your data. You can call it anything you want, but I prefer to call it Wild Dog, just like the name of the CSV file. CSV stands for comma delimited, which is a special type of format that any computer can read, because not all computers can read Excel. It's a proprietary software. This is what Kenny used to get his file path for Wild Dogs. I need to find my file path. So you can see here, I have Wild Dogs. In Macs, you would get info, and I can see that it's saved in my iCloud drive and desktop. So I just copied it, I would paste it in here, and you can see I have my file path, but it didn't quite get the file name, so I have to include the actual file name, which is wilddogs.csv. Now it's very important, always use the correct capitalization when you work in R. R actually cares about this. So now I'm going to click Run, which is right up here. You can see that down here, my code was run, and now Wild Dog has appeared in the environment. When I double click on Wild Dog, it opens the actual file, and you can see the name of my variables, as well as the data that's stored within it. Now, this is not always easy for everyone, as it can be really difficult to find the file path. So for those of you who are having difficulty opening the file that way, you can try. This is just a new name of data, but you can try to read the CSV file from a file.choose, and we're just going to tell it here that the headers of the columns need to be maintained as headers in our data file. I'm going to run this code, and then what you'll see happen is that it actually lets me go in and choose my data itself. So I save mine to my desktop. You can see that right there. I'm going to open my CSV file, and if you look at the environment, Wild Dog 2 has now come up as my observations. So I'm going to attach my data so that R knows how to run it, and everything is great. The next thing we need to do is build a summary table. So I went back into Kenny's RTutorial, so for those of you wondering what I'm using, it's this part. And I need this line of code here. I'm going to paste it into my RStudio like this. You should have already installed these packages in class, so if you run the library, it should run in the console below. Kenny wrote this script. Never mess with this script. Never mess with this script, because it already does everything for you to make a summary table. All you have to do is run this line of code, and you'll see that now that function exists in your environment. Using the RTutorial again, we're going to use the code to actually make our summary table. Here you can see that the function is data summary, just like the one that you built in your environment. Well, we are going to tell it that we need our data, which I named wild dog, our dependent variable here, which is aggression, and our independent categorical variable, which is dominance. So, dependent, then independent categorical. However, I don't really like this name. I don't think it does a lot to tell me what df2 is. So I'm going to rename this output as wilddog.sum for wilddog.summary. So let's see what happens when I try to run this code. Oh no, I got an error. It's telling me these objects aren't found. Well, this has to match your file. So if we open that file again, you'll see that the columns are not called dominance and aggression, but rather dom and ag. So I have to go back in here and call them ag and dom. Now when I run it, you can see that the code ran without error, and now my wild dog summary is actually saved here as another file. If I want to see what that looks like, I have to print it. But df2 does not exist in my data set here, so I have to specify what I specified here. I have to be consistent, wild dog sum. When I run this, you'll see that I get this summary table in my print below. I can also click on wild dog sum, and now I have it here as well. Now for your summary tables, you are actually going to need to put them into a Word document. So I'm just going to quickly show you how you can make a Word document yourself. So here I have Word open. I'm going to insert a table, and I want my table to be a 3x4 table. So I just click that, and now it's there. This column is going to be dominance levels. And I'm just going to call it alpha, beta, and omega. Let's be consistent here, right guys? Okay, now what was the responding variable? What did we calculate here? Well, these are means or averages. So I'm going to go average aggression rate. But that's not enough, right? We have to remember our units, which is the number of aggressive acts per individual per hour. And we also have the standard deviation for those aggressive acts. You can then just copy and paste in your values. Oh no. You can copy in your values, or you can just write them yourself. For instance, we like to go to 2 decimal places. I'll say 1.93, 1.47, 0.77, 0.51, because that 5 rounds to a 1, 0.77, and finally 0.25. Now, this is okay as a table, but it's not great. So there's a couple things we're going to do. When you go to table design, you'll see that there's this column borders. We want to have no border first. So you want your entire thing to, table to look like this. You then want to select just your top row. You can just highlight it. You're going to go to borders and then bottom border. You also want to select your last row, go to borders again, and select bottom border. This is what we expect for tables. You want to minimize the amount of lines on it because otherwise it looks ugly. Now, to make sure that this table fits into my Word document properly, I might have to do a special thing to my table called autofit. You can see there's an autofit here, and you can select autofit window and it'll automatically fit it to the window. So if you had it way off the screen like this, you just got to click your table, autofit, autofit window, and now you have it back. And that's how we make a table. It's also important to remember that your table has to have a title. So you need to write table 1 and your clear and specific title goes here. Yay! So that's how you would insert your data into a table in Word document. So you can close this here. We've made our summary table. We have our data for our means. The next thing you need to do is make a bar chart, right? Because this is independent variable equals categorical. We need to make a bar chart. Okay, bar charts plot means. Where are the means? In your summary table. So going back to the RTutorial, I'm going to copy Kenny's code for bar charts right here. First, I need to run this library. This library is called ggplot2. This just lets me make an entire bar plot. This is the actual code for the bar chart. Here, this P, that's the name of the graph. I can name it whatever I want. I don't really like P, so I'm going to call it wilddog.fig, like wild dog figure. You then want to have it keep this the same for the function, but you'll see here that it's df2. Now df2 is that df2 that I changed up here. It's my summary table. So you want to make sure that you use the summary table to get the means for your bar chart. Now if I look here, it says the x variable is dominance, and it is, except that's not what it's called in our data set, right? It's called dom and ag. So I have to change these to dom and ag. As well, you'll see that we have error bars in here, where it says aggression minus standard deviation and aggression plus standard deviation. So I have to change this part to ag as well. Now I'm going to run this, and you'll see that it came up in my environment as well. So I know it worked, and there's no error in my console below. So now I want to print my figure, so I'm going to go wilddog.fig and run it. You can see that we get a graph right over here, but this graph is ugly. Ugly. So, how do we make it pretty? Well, going back to the RTutorial, I copy in this nice line of code right here. This P is the name of my graph, which I called wilddog.fig, and I need to label my x variable whatever I want. So instead of saying dom, I want it to say dominance levels. Instead of saying ag, I want it to say average aggression rate or acts per individual per hour. When I run this code, it changes my graph into this beautiful graph you see now. This is the type of graph that we want you to submit. Now to actually get your graph out of R, you can go to export and save as image. You want it as a PNG file, and here you'll see you need to go to the directory. You have to tell your computer where to save it. So I'm just going to save it in my desktop. See, now it says desktop up here. And I'm going to change the name of this file to be wilddogs.fig or underscore figure. And I'm going to save that, and it should open. So now it opened as a separate file. You can see that here. I'm just going to move this here. And when I go into my Word document, you will see that I'll be able to just add my figure in. Okay, but our figure is not done. You need to also add a figure caption. Notice that table captions go above, figure captions go below, and we would put our clear and specific figure legend below. Yay! So now we've learned how to make summary tables and bar charts for data. We can practice this on another set of data. So let's go File, New File, RScript, and let's save this as Sunstar. Now, if we think about the Sunstar data, our independent variable is also categorical, and it's two groups. So we can follow a lot of the same steps because we're also trying to build a bar chart, and we need means from the summary table. So what do we need to do first? Open the file. I can go to my wild dogs file, and you'll see that I already have all this information about how to open my file. But instead of calling it wild dog, I'll want to call it Sunstar. So I've changed all of this to be Sunstar. However, if you look at my CSV, it's still set to open the wild dogs. I need it to open my Sunstar. Because I saved my file in the same place, all I have to do is change this file path. When I run it, you can see that it opened here, or I can just do the same thing as I did before and have it let me choose the file itself. Sunstar.csv. See? And I'll just attach that data again. And if we open Sunstar, we can see our lengths and our time. So time is ocean conditions. And what I want you to notice is that current is the first categorical variable in the column, and future is the second categorical variable in the column. So now we have our Sunstar, right? So the first thing we have to do is we have to make a summary table. Well, when we did our wild dogs data, we first ran the code to actually build a summary table. But we don't have to do that again because I still have that function here in my environment. If I didn't, I would have to rerun this code. But because I already did that, I can just take this and try to build my summary table. In this case, I want it to be called Sunstar, and I'm making sunstar.sum, and I'm going to take my data from my Sunstar data. Now, our variable, we need our dependent variable. What's our dependent variable? It's length. And the name of our groups was time. So what happens if I try to run this code? Oh no, there's an error. It says Sunstar is not found. Now what you might see is this Sunstar has a capital and this Sunstar does not. So I'm going to make this Sunstar lowercase and see if that works. Yay, it works. So now you'll see that I have my sunstar.sum and I have all the things I need to make my summary table. So that worked out well. You can also print your sunstar.sum table and it'll come up in your console below. So the next thing I need to do is I want to make my bar chart, right? So let's go back to that wild dogs data. Well, this is how I made the figure for Sunstar, right? So I'm going to go here and I'm going to make my Sunstar figure with my Sunstar summary data. Notice that it's summary data, not the original data. Now, if my x variable is this and my y variable is this, what's going to happen? And let's print this figure, sunstar.fig. Oh no, what happened here? This doesn't look right. Look how weird this looks. Now, if you guys were paying attention, you would know what I did wrong. This, current and future, that was actually our x variable, and length was our y variable. Notice that I put them in the wrong places. My x is actually time, and my y is length. So what you can do is you can actually delete this graph by clicking this remove current plot. So you see, I did that. Now I'm going to run this line of code again. I'm going to print my graph, and you can see, oops, I also forgot to change my error bars. So now I do that, and I print, and now we have the proper graph that we want. I want to make it pretty, so I'm going to go sunstar.fig. Now I want to change my x variable. Our x variable wasn't time, right? It was ocean conditions, pH. And my y variable wasn't average aggression rate, but average length in millimeters. So I'm going to run this code, and now I've got a pretty graph, and I could export this data as well. If I want to take a look at the other graph I made, I just have to click back into the arrows, and they'll show up over here. So now I can see all the ones that I've made, but this is the one that I like the best. So yay, we've made our graphs for 2 data. But now let's take a look at a different scenario. Let's save this again. I'm going to save it as sundew. What happens if our independent variable is numerical? We have to build a scatter plot. But the first thing we have to do is open our file. And we can follow the same thing that we've been doing this whole time. I can go over here, call this sundew, change my sundew here, check how I say it. Notice that the D is not capitalized here, so I'm just going to go sundew, run that, and it popped up in my environment. I can click on it, and look at that, I have all my data right there. And again, if you're having difficulty, you could try it this way and just manually find your data in the computer itself. And so we want to make sure we attach that data. Okay, so now that we have this data, we want to make a scatter plot. Scatter plots don't use means. They plot all points. So no summary table required. We can just go straight to our RTutorial to grab the information for the scatter plot. So this is the information for the scatter plot. I copied it, and I'm just going to paste it in here. And we can see this is the name of the graph. I don't like P2. I'm going to call it sundew.fig for figure. This is my data. It matches the name of the data here. It says that the X variable is phosphorus, the Y variable is photosynthesis. Now wait a minute, I've made mistakes before. This X and this Y are correct, but are they named right? Nope. I better make sure that I change this to phos and this to photo. Okay, is there anything else I have to change? No, there's nothing else that I have to change as part of that graph. The next thing I have to do is print my graph so I can actually see it. So I'm going to print my graph right here, and you can see it popped up in my environment here. Well, this graph is ugly, right? So I'm going to go and I'm going to change this to sundew.fig, and we're going to look, yes, phosphorus is percent dry rate, photosynthetic rate is this. If I wanted to change it, I could. And I'm going to run this, and wow, look at how amazing this scatter plot is. So that's great. Congratulations. I'm going to write congrats. You made all your graphs. So let's move on to statistics. Well, one of the simplest statistics is categorical, or when your independent variable is categorical and you have 2 groups. Our hypothesis can be two-tailed, which is there is no significant difference in average sun-star larvae length between current and future ocean conditions at 15 days post-fertilization. So a very long two-tailed hypothesis, okay? And what we would do is if we have a two-tailed hypothesis is that we're going to run a two-tailed t-test. In this case, it would be like this. T-test calls the function, and I'm looking at response. So let's copy and paste this. I'm going to add a hashtag here so that it doesn't run this. But this is always your dependent variable, and this is always your independent variable in a t-test. The alternative specifies what type of hypothesis you made. Well, we made a two-tailed. So let's see what happens when we run this. Wow, so you can see the data down here, and I can see that the p-value is very significant. So let's take a look at this graph. It's telling us that either the future conditions either increased in length from current conditions or decreased in length. We don't know which direction because we were looking for any direction. Any direction is significant. Remember that 2.2e to the negative 16 is below 0.05, okay? So what happens if we want to do one-tailed tests? Well, we have two options. Remember that in the scenario, lengths of larvae decreased in future ocean conditions with planktotrophic larvae. So the way that we would write that one-tailed hypothesis is there is a significant decrease in sunstar larvae length when raised in future ocean conditions. Here you would put at 15 days post-fertilization, gotta be specific, when raised in future ocean conditions compared to what? Compared to current ocean conditions, okay? So what we now have to do is we have to specify in our t-test what direction we want our data to go. When you do direction, it always compares to the first group. If we look at our sunstar data, the first group is current. So if we want to ask if the future, the lengths decreased in the future, then we are asking, let's get this here. If we think future decreased, we need to ask if current is greater than, current length is greater than future length. So when I edit this hypothesis, I would write greater. So let's run this t-test. Now what you'll notice is the p-value is 1. That means that this is not significant. So here our p-value is less than 0.05. We reject the null and conclude there is a significant difference. For this one, the p-value is greater than 0.05, so we fail to reject the null and conclude that there is no significant decrease in future length compared to current. So in the future, they didn't decrease. If the larvae length didn't decrease, could it have increased? That'd be weird. Well, let's see if it did. So thinking about our one-tailed hypothesis, first we asked if there was a significant decrease. Let's ask if there's a significant increase when raised in future conditions compared to the current. Because we're always comparing to the first group, and that first group is the current future condition, okay? If we think the future increased, we'd have to ask if the current length is less than future length. So we would take our t-test and we would change this to less. Now what happens when we run that data? You'll see that the p-value is significant. So what we're going to say is that the p-value is less than 0.05. We reject the null and conclude that there is a significant increase in length in future conditions. So you wouldn't just write a small thing like this, you would actually write out your whole conclusion. So write out the alternative hypothesis completely again as your conclusion, okay? So now we finished t-tests. We found everything that we could possibly know about this. Let's try the wild dogs, because our wild dogs is also an independent variable that's categorical, but now it's 3 groups. So we got to do an ANOVA. Let's go back to the RTutorial and find the data, the code for an ANOVA. Now this is our code to run an ANOVA. Remember that this is not our regression is labeled in the actual data file. We have to make sure that this is ag and this is DOM. So remember that for this code, and I'm going to hashtag this again, it's summary AOV, your dependent variable to your independent variable, or your groups. Okay? So summary, AOV, ag, DOM, and we can look at what we found below. And so this is all the information. So you can copy and paste this output. You can copy and paste it into a Word document. I just copied it and show you below. I can paste it into a Word document and highlight my p-value, right? And this p-value, oops, I don't want to write this here. Be careful. Make sure you try not to write too many things here. You might mess up your code. Let's go here and go say, as a reminder, my p-value was less than 0.05. Therefore, I reject my null and I conclude my alternative hypothesis. Well, let's take a look at that graph again, right? My conclusion is there is a significant difference in average aggression rate between at least 2 of the 3 dominance levels. So this between at least 2 of the 3 is really important because we can't figure out from this information which group is different. Now, if we look at our graph, we can take a look at that standard deviation. And what you might notice is that the alpha standard deviation doesn't overlap with the standard deviation of the mean around omega. So my guess is that alpha and omega are probably the ones that are different. If you then look at alpha and beta, there's a lot of overlap of the standard deviation spreads over those means. And the same thing for beta and omega. So it actually looks like beta and alpha aren't different and beta and omega are different. And the difference is only between at least 2 of the 3 groups. Okay? And there you have it. Done. We've already interpreted our ANOVA. 2 tests down, 1 test left. Now the last test is for when your independent variable is numerical. In this case, we have to run what's called a linear regression. And so if I went to the RTutorial, I can find the linear regression information here. This is just whatever you want to call your model. So you know what I'm going to call it? I'm going to call it sundew output. This is my output. The LM is the function. L stands for linear, M stands for model. Now what happens when I run this? This object isn't found. If you guys are following along, I did something wrong. I forgot that these are actually labeled FOSS and photo. So I'm going to go in here, I'm going to label photo, I'm going to change this to FOSS, and then I am going to run this code. Now it has run my linear model. So you can see it came out in my values. If I want to find out what was in this value, I'm just going to write the summary of my model or the summary of sundew output, and I'll get my information below. So I'm going to copy and paste this into a Word document so that we can talk about it. Okay, so this is my, this here is my linear model output. I'm going to find the graph scatter plot again for us. Oops. Ooh, I went a little too fast through it. It didn't like it. but that's okay. So now we can see this graph. And if we were just looking at this graph, I mean, a lot of the data points here are pretty close, but there are some pretty far data points around the far edge. So I'm looking at my linear model, and I'm looking at the p-value for phosphorus. So this is phosphorus. And what you can see is our p-value is significant. So if I was going to talk about this, I'd say my p-value is less than 0.05. I reject the null, and I conclude that there is a significant linear relationship between phosphorus content and photosynthetic rate in carnivorous sundew plants. Okay? So that's one thing that we can conclude from the output that I got from R. Another thing that we could look at, I'm just going to highlight it in a different color so you know what I'm talking about, are these estimates, these estimates at the front. Remember that the equation of a line is y equals mx plus b. So if we were trying to find our slope, well, our slope is for the x variable, and it's about 7.49. And what's our intercept? So slope is m. What is our intercept, or b? B is about 0.99. So that's our intercept up here. So if I had to write it, y equals 7.49 times x plus 0.99, or if I was going to write this in words, the photosynthetic rate is equal to 7.49 times the phosphorus content of leaves plus 0.99. How do I write this equation in words? Well, we have to think about our slope. What's happening here? Well, notice that the slope is positive. So I'm going to write, as phosphorus content in leaves increases, photosynthetic rate also increases, but I don't stop there, by a factor of 7.49. That's our slope. And we can also look at our intercept. So intercept is what happens when x equals 0. And I can write about this and say, when no phosphorus is present in the leaves, the photosynthetic rate is 0.99, what is the unit here? Micromoles per meter squared per second. Okay, and that's how we would write about this equation in words. Now there's one more important part of this output, and that's our r squared. And our r squared here is 0.51. And it's asking, how good is that line at predicting, or how good does this line fit our data points? If this was good fit, all the data points would be really close to the line. If this was bad, the line would probably be straight and all the dots would be far away. However, you can see we've got some that are close and then some outliers and a little bit of messiness over here. So, I mean, it's okay. It works slightly. How would we accept this as ecologists? Yes. Anything better than 0.30 is good because there are so many factors that affect our system. How do we talk about the r squared? Well, we would say that phosphorus content explains 51% of the variation around the mean in photosynthetic rate. And basically what this means is that when you find the mean photosynthetic rate for these plants and there's a lot of variation, 51% of that variation depends on the phosphorus content of the leaves. So this is how you would run all of the class examples that we did, how to get graphs and ANOVAs. Hopefully you can work with this to finish answering the questions on your assignment. If you still have questions, there's a couple ways that I want you to reach out to me. I want you to screenshot your error code from the console below. So if you get something like this, I want you to tell me what the error code is. Okay, then I want you to attach the R script. So you see how we have, I saved this and it's .r. I want you to send me the .r file. And finally, also send me the data that you are using, just in case it's the wrong one. I hope that helps. Have a good week.